I'm start the recording. Bismillahirrahmanirrahim. Assalamualaikum. Today is 11th November 2020, 9 p.m. Basically, that this is the replacement for the this morning class that I couldn't make it, and today we are going to go through the topic on this frequency response and body plot. Okay. Any questions so far on Laplace transform, Fourier transform, Fourier series, convolution, and systems and operation? Those are the things that we have covered so far. Apa tu?
No, sir.
Tak ada. Okay.
No.
So, semua clear ke? Semua boleh faham ke?
Kena ulang kaji sikit lagi, sir. InsyaAllah faham.
Betul, sir.
Okay. Nanti kita buat ulang kaji. Okay. Basically tomorrow we want to have class from 9 to 10 ke nak on Friday? Hopefully, I rasa I nak tambah 1 jam for this week. So maknanya tonight is about one hour, about 2 hours. Tomorrow about 2 hours or 1.5 hours, and another 1.5 hours. For me to do the revision with you, tutorial.
Okay, sir.
So besok pagi. Besok. 9
Pagi.
Start from 9 besok. Okay.
Alright, sir.
Okay, now I'm share the slide. Okay. Do you see the slides? Frequency response and body plot.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Frequency response and body plot. This is in chapter 9, Navi textbook. So this is what we're going to cover. Introduction on frequency response and body plot, transfer function, frequency plot, and body plot. So very short one. What is the frequency response? Frequency response of a circuit, basically that it describes the relationship between the amplitude and phase angle of the input and output sinusoids. So basically that is a response of a circuit with regards to the input and output. The signal that's going in and the signal is going out. So what is the response? And common application is basically that is, for example, is the in filtering, or filter design for electrical circuits. There is a simple example. Another example is the control systems, a control transfer function. You have signal in and you do something, a control transfer, control transfer function and the output. So the transfer functions is for the you have the frequency response for that. So in this chapter we are going to cover the first order and second order circuits only. So we are not going to cover the third order and whatnot. So only first order and second order. So how to determine the order of the circuits? Whether the circuit is first order or second order. Basically that in order for you to determine whether it's first order or second order, you look at the circuit itself. What are you look at the storage elements, the L and C's, the inductor and capacitors. So that's how you check whether it's first order or second order. First order circuits, basically that you have RC or RL. You only have one storage element. So that is the first order circuits. For example, in this case, you have what do you call it? You have the inductor and you have the resistor. Okay, so this is RL circuits. So this is a first order because you only have one L. You only have one storage element. Right? So you can also have the RC circuits. Right? You can also have RC circuit for the first order. So this is the example of first order. For the second order, basically that you have two what do you call it, storage elements. Or if you have an equation that you have 1 over s plus something multiplied by 1 over s plus something. So, or 1 over s square plus bs plus c. So that is a second order, right? So for body plot, a body plot is actually that is a graph of a transfer function of a linear time invariant system versus a frequency. So it's a graph of h of s or h of j omega. Right? So there is a plot of this, a graph of that, which is with respect to the frequency. So this is frequency, right? And the vertical axis can be magnitude, right? Or phase, right? So this is phase, this is magnitude, okay? And the horizontal axis is the frequency. Right? So that is the plot. And normally that for the frequency, we use the log scale, right? You use the log scale, right? Instead of linear scale. And on the vertical axis, you use a linear scale, right? So body plot, normally that you plot on a semi-log graph paper. It is usually a combination of body plot of a body magnitude plot expressing the magnitude of the frequency response gain and the body plot expressing the frequency response phase shift. So h of s basically that you plot the magnitude and also the phase component of it. Okay? So in this example, basically that is the high pass filter, and body plot is actually a plot of asymptotic plot, not the actual plot. This is actually the red one is the actual response. Okay, but the body plot is actually the straight line. So the straight line, where at this corner here, at this knee, we call it knee, lutut. At this knee, it's normally about 3 dB drop. So this is where you have a 3 dB drop between the asymptotic plot and the actual value. It's about 3 dB. Okay? 3 decibel. So that is the body plot, and then introduction to the body plot. So any question on the introduction? What is frequency response and what is body plot. Very simple. Now we are going to go into the transfer function, into more detail in what is the transfer function. So the transfer function, normally that we use a symbol of h of s. Use symbol of h of s, or in a steady state, use h of omega, or h of j omega, where s is equal to j omega. Okay, so there's the symbol. How to find h of s of a system? There are 4 ways. When it exists, the system function may be obtained from first one is input-output pair. And this system impulse response, system's unit impulse response, or input-output differential equation, or frequency response of the systems. Input-output pair can be V out over V in, or I out over I in. So this pair, the input pair and output pair. The impulse response is basically that you have a system and maybe you pump in the delta T and look at what is the output. This is h of t. So that is also, you can have the h of t, h of x. This, the system unit impulse response. Also from this differential equation. This one actually you learn from the calculus differential equation on math, and also the frequency response. So all these 4, basically that you will give you the same result. And for our case, normally that we use this number 1 or number 2. But in this course, we use the number 1. So h of s is a ratio of the phasor output voltage to the phasor input voltage. It's a function in frequency. So like h of s is equal to V out over V in, or I out over I in. Basically, this is tinggal s, function of s. Okay. Phasor is a complex entity, consists of both magnitude and phase. So basically that you have h of s, which is the magnitude, and also the phase of the h of s. So you have both components, the magnitude and the phase. What is the magnitude? The magnitude of a transfer function is the ratio of the output amplitude to the input amplitude. So basically that is either V out over the magnitude of V in, or the I out over the magnitude of I in. Whereas the phase of the transfer function is the output phase minus the input phase. So this is minus, whereas the magnitude is the ratio. Ratio is for the magnitude, and the difference is for the phase. So basically that you have the phase of the output minus phase of the input. Macam mana lah saya punya ni, jadi ada line-line macam ni. So the magnitude and phase basically tells how the amplitude and phase of each frequency component are affected by the network. So it's actually indicate how the input basically that how the magnitude of the x of the input will affect by the system which result into the output. This. So how does it affect? Whether is scaling increase, whether is decrease, whether is shifting or what, whether is increase or decrease for the magnitude. For the phase, then is whether it's you have the phase shift or not. What happens to the phase of the input when it goes through the systems. So the magnitude and phase basically that tells the relationship, the affected component by the network, by the systems. Example of a transfer function. Let's say the response of system to a unit step input is measured and modeled by e to the minus at ut. Assume an LTI system, find its h of s. So you have what do you call it? The input, and you have the output. So the input is u of t, this unit step input, and the output is given by e minus at ut. So now you want to find here, you want to find what is this, and now basically that we want to find the h of s instead of h of t. So u of s, this is what we call x of s, and this is y of s and h of s. So u of x of t, x of s is actually the transfer function of x of t. I mean the Laplace transform, right? Because we use this x of t convolve with h of t is equal to y of t. So therefore, we use Laplace transform, so you get x multiplied by h of s is equal to y of s. So h of s is equal to y of s over x of s. Okay. So we have to find this y of s and x of s in order to find the h of s. So what is x of s? X of s is actually the Laplace transform of x of t. The Laplace transform of unit step function is actually 1 over s. This actually you get from the table, right? 1 over s, x of s. What about for y of s? Y of s is a Laplace transform of y of t, which is y of t is e minus at ut. So you take the Laplace transform of e minus at ut, you get y of s is equal to 1 over s plus a. Okay. So h of s is basically equal to y of s over x of s. This is equal to 1 over s plus a divided by 1 over s. This is equal to s over s plus a. So that is the transfer function for this system. Right? Clear? Boleh?
Boleh sir, boleh.
Okay.
Boleh sir, boleh.
Yeah. Example number 2. Let's say you have a circuit, RC circuit. Okay? And you need to find the transfer function of these circuits. So the transfer function is given by V out over V in. So in this case is V2 over V1. Right? So what is V2? V2 is actually you can use a voltage divider, which is V2 is equal to the impedance of a capacitor divided by the total impedance. Impedance of capacitor divided by total impedance, which is R plus ZC times V1. What is the impedance of the capacitor? Is 1 over SC. Okay, this is the impedance of the capacitor. Okay, so 1 over SC divided by R plus 1 over SC V1. Okay, so you simplify, you get 1 over 1 plus SRC RC V1. So therefore, your transfer function H of S is equal to 1 over 1 plus SRC, or it can also be written as 1 over RC plus S. Right? Under steady state, S is equal to J omega. So this what we call it, sigma is equal to 0, right? So under steady state, H of S equal to V1 over V2 is equal to 1 over 1 plus J omega RC, because we just substitute the S with J omega. So therefore, the amplitude of H J omega, you get 1 over square root of 1 plus omega RC square. And the phase is equal to minus arctangent omega RC over 1, right? So this is actually, you can go through the math, right? So you get this. So from here, basically you can get, so this one you have to do it on your own, right? Can you do this? Can you get this? Phase and magnitude on your own?
Boleh.
Boleh. Okay. So that is the transfer function for this network, right? So this is the transfer function in S, and this is in steady state, where it can also be written in terms of magnitude and phase, right?
Baik sir.
Okay, another example.
Sir, nak tanya
So,
sir.
Yes,
Kenapa dia negatif tangent tadi?
this
Ha.
one.
Yang belakang
This
tadi.
one you have to,
Yang ni.
this one you have, try to do it on your own. Boleh?
Oh. Okay.
But why?
Try dulu. Try to do on your own. Okay. This is the angle, the phase. What's the formula for the phase?
Nah, the face Phase output minus phase input. Oh.
Yes. What is the phase of output?
Phase of output. Entahlah. Macam mana Phase of output. Entah. Apa? Saya pun tak tahu. Ni apa warna
In
ni?
tolak out.
Apa yang in tolak out? Apa
Try
tu?
to work on your own. Macam mana? Okay?
Alright, sir.
Try to do on your own, then tomorrow we'll see. Okay?
InsyaAllah.
Tomorrow we'll see. Okay? Okay, example number 2. Given the transfer function of a network as h of s is equal to s times 10 to the power of 10 divided by s squared plus 200s plus 5 times 10 to the power of 6. So, what order is this? What
Ini
order is this?
order.
Transfer function.
Aha.
First order, second order, or third order?
Ada S. Tak tahu macam mana.
First order.
Second kot sir,
Second sir, sebab S to the power of 2 tu tahu.
Tu saya circle tu apa benda? S to the power of 2 is a second order.
Oh.
Yes sir.
It's a second order.
Second. Okay. Alright.
Wait, the transfer function at omega equal to 1000 radian per second and at 3000 radian per second.
Second.
So this is very simple because we just plug in the value, right? At omega equal to 1000 radian per second. So first, actually you rewrite this h into j omega equal to j omega 10 to the power of 4 divided by j omega square plus 100 j omega plus 5 times 10 to the power of 6. Then you substitute the the omega with 1000. So you
1000.
get this equation. And
Yes,
you simplify, and
J.
so you get 10 to the power e j to 90 degrees divided by square root of 20 e j 26.6 degrees. So you get the magnitude of 2.24 and phase of 3.4 degrees.
Sir, dia buat proses apa tu sir?
Ha?
Dia buat proses apa daripada J tukar jadi E tu?
That one is the steady state.
Oh, steady state.
Steady state.
Yeah.
Yes. Because S is actually equal to sigma plus J omega. But for steady state, S is
Zero.
equal to J omega. Right? So this is the steady state. S equal to J omega. And for the second one, omega equal to 3000 radian per second. So you just plug in omega equal to 3000 into the equation and you simplify, you get 4.16 e to the minus 33.7 degrees. So the magnitude of 4.16 and phase of minus 33.7 degrees. Right? Okay.
Alright sir.
Now, find the frequency response of the system below at omega 1 equal to 1000 pi, omega 2 at 3000 pi, omega 3 at 5000 pi, and omega 4 at 7000 pi. Given that R is equal to 200 pi ohm and L equal to 0.71 Henry. So from this circuit, you
First order.
get the transfer function.
Oh, okay.
Transfer function is basically that the voltage divider between the resistors and the inductors. Right? So it's a V2 over V1. Right? What is V2? Is IR.
Yeah.
So whatever lah. So basically this ZL plus R is the Z equivalent. So you use the voltage divider, is equal to R over R plus ZL times V1. So V2 over V1 is equal to R over R plus ZL, where ZL is equal to L. Okay, that's why you get this. H of S equal to V2 over V1 is equal to R over R plus SL. Okay, and you substitute S equal to J omega. So this H J omega equal to R over R plus J omega L. Okay. Then you rewrite in this format. So you get 1 over 1 plus J omega over R over L. R over L is known as the frequency omega C. So you can write as Hj omega equal to 1 over 1 plus J omega over omega. Rewrite like that. So the magnitude is equal to 1 over square root of 1 square plus omega over omega C square, and the phase is actually minus arc tangent omega of omega C. So now you use this formula find the response of the omega 1, omega 2, omega 3, and omega 4. Right?
Sir,
Yes.
tak berapa nak faham lah. Macam Melayu sangat lah yang omega J omega L tu kan. So ayat apa yang jadi tu 1/1 apa ni?
Okay. ZL you tahu? Is SL.
SL.
J omega L.
Okay.
Right?
Alright.
So this is actually you don't know how to get this.
Don't know.
Don't know. Okay. You look at these circuits, right? V1 is the input and V2 is the output.
Okay.
So what is the V2? V2 is the voltage divider between these two components, right?
Okay.
So this is actually ZL. This is R. So Z equivalent is equal to ZL of plus R, right?
Okay.
So what is V2? V2 is the voltage divider, which is V2 is equal to the resistance here, the impedance here, which is R, divided by the total impedance, right?
Okay.
So this is ZL plus R multiplied by V1. Okay. Clear so far?
Clear.
Okay. Now, what is the transfer function? H of S. H of S,
Input
the transfer
over
function is the ratio of the output
and input.
over input. So in this case, ratio of V2 over V1. Apa ni saya dah buat ni? Macam mana nak tu?
Macam mana ni boy?
Sekejap. Okay.
Ayah.
So V2 over V1. So you get this R over R plus SL.
Oh.
Okay.
SL. Oh. Okay.
This part is actually ZL. This. The impedance of that.
Okay. Okay.
Then this in S in S domain. So you convert into J omega domain by changing S to J omega. So you get this. And this actually you just do the manipulation of dividing by R. You divide the top one by R, the bottom one by R. So you get 1 over 1 plus J omega L over R. And this can be written as 1 plus J omega over R over L, where R over L is known as corner frequency, omega C. So you can just plug in the.
R over L.
Dia memang kena ganti
So in this
sampai
case, omega C.
So dia memang kena ganti
This
sampai omega C. Oh.
Since you know the R and L, you can just multiply. But that you can do this here.
Oh.
Okay. Yeah. Can I continue?
So kalau tak ganti dengan omega C boleh tak?
Boleh.
Sampai HJ omega biasa.
Boleh.
Saja. Oh, okay sir.
Sampai kat sini. Lepas tu you just substitute RL, R and L into the equation. So you get lah the value. Can. Then after that you use this value omega 1, omega 2 to substitute into omega, find the magnitude and the what do you call it, the angle, the phase. So you plug in the value of this, then you get this the answer.
Okay. Sir, yang
you don't know how to get from here to here. Hello?
Hello. Siapa tu?
Dengar tak?
Dia
Yes.
sangkut.
Pecah-pecah.
Hello. Sir, saya sangkut-sangkut sir.
Dengar saya tak? You dengar saya tak?
Dia bunyi macam ni sir. Oh, mega.
Oh. You dengar saya? Saya dengar you clear.
Dah clear sir, dah clear.
Okay. So basically that now you have this transfer function, right? So you have, if you don't want to use the omega C, you can H J omega equal to 1 over 1 plus J omega over R over L. What is R over L? Which is
frequency
200 pi divided by 0.1.
Oh.
200 pi divided by 1, 0.1. So basically you get 2000 pi, right?
1005. Okay.
2000 pi. So omega over 2000 pi here. Right?
Oh.
So then omega here, you just substitute with 1000 pi for the omega 1. Then you do the calculation. So you get this answer.
R over
Okay.
L omega C.
Okay.
Okay, insyaAllah boleh.
So for the basically H J omega equal to 1 over apa tadi? 1 plus J omega over tu 1 plus J omega over R over L. Okay. So R over L is 1000 pi. Okay. R over L is 2000 pi. Basically, your equation that you have to work with is H J omega equal to 1 over 1 plus J omega over 2000. Okay. So omega equal to 1000 pi. So you get 1 over 1 plus J. Okay. Right, for this one, this is the H. 1 over 1 plus J.
Sir masih dekat slide yang sama ke sir?
There, no.
Oh ya.
This is,
Okay.
so I use this slide.
Okay, okay.
Yeah.
Alright.
Okay.
Oh,
This for omega 1. For omega 2, for this one, basically you have H J omega equal to 1 over 1 plus, what is omega? Omega 2 is 3000 pi plus J 3000 pi over 2000 pi. So basically 1 over 1 plus J 3 over 2. So you find the magnitude for this and the angle, so you get this answer. What is the formula? Here. This. So basically for that one is 1 over square root of 1 square plus 3 over 2 square. Then you get this 0.55 here. So for this 1 over 1 plus J 5000 pi over 2000 pi. So 1 over 1 plus J 5 over 2. So the magnitude is 1 over
Kita kena cari phase dengan magnitude dia.
yes,
Oh, okay, sir.
phase and magnitude. Okay, this is in this form and this is in polar form. Okay, phase and magnitude.
Oh, betul.
Okay. For this one, basically is 1 over 1 plus J 7000 pi over 2000 is equal to 1 over 1 plus J 7 over 2. Then can be written in this form. So you get magnitude of 0.227 and phase of minus 71 and minus 74.1 degrees. Okay. Clear?
Clear.
Suara saya putus-putus ke?
Okay.
Okay. So that is with regards to the transfer functions. Now we are going into the next topic, which is a frequency response plot. How are we going to plot the frequency response? All right. So h of omega can be shown in several ways, some of which are: one, you can do a magnitude and phase plot as function of omega. So you can do as what I have shown in the first plot, right? Or you can do in magnitude and phase in the format of polar plot, which is you in the vector format. And third, you can do a plot with a real and imaginary part as a function of omega. So in this course, we'll be using the magnitude and phase plot. So we are going to use the number 1 only. We are not going to use number 2 and number 3. But in your textbook, it has the example for number 2 and number 3, just to show you what the difference between those two. Right? Okay. This is actually.
Okay.
Sir, slide sir dekat example 4 lagi ke sir? Ke kita nak punya?
I go to the next one already.
Sir punya lag.
Lag ah.
Lag. Ya, betul.
Dah ada.
Tak gerak sir.
Belum.
Nampak tak?
Belum.
Belum.
Macam mana ni? Main kot, tak tahulah.
Sebelah ni sir, ramai orang pakai internet kot.
Okey, nampak tak?
Belum sir.
Belum. Sir. Joy Orin. Joy.
Okay.
Apa?
Dah.
Dan jambu batu. Tetrit.
Dah ada. Nampak belum?
Belum sir. Saya nampak example 4.
Nampak example 4.
Baik pun sir.
Kejap
Tak apa sir.
Saya pergi ni. Okey. Saya unshare.
Tapi suara sir dengar tu yang pelik tu.
Clear kan?
Oh, suara dengar.
Okay. So I reshare. Nampak tak?
Ustaz.
Nampak tak?
Nampak. Frequency response plot.
Okay. So frequency response plot, H omega can be shown in several ways, some of which are magnitude and phase plot as function of omega. So for this one, basically that you can plot using the frequency here or omega, and this is the magnitude of H, and also this is, you can do this omega and phase. So this is actually maybe plot something like that. So this is the plot of magnitude and phase, the one that I showed in the earlier slides. So the magnitude and phase in the polar plot, it can be shown in form of let's say this is 0 degrees here, okay, and this is 90 degrees. So let's say if it's 45 degrees, it's in the form of vector. Okay, this is the length of the vector is the magnitude, and this is the angle theta. So that is magnitude and phase in the form of polar plots. The plot of real and imaginary, a function of omega, basically that you have the this is the real part, this is the imaginary part. So you can plot maybe something like that. So maybe 1 here, and this is J3, for example, 1 plus J3. So the point is maybe here. So you plot the real and imaginary. But for this course, for this subject, we only do use the magnitude and phase plot. So we are going to use this only. So we are not going to use this and this. Okay. Simple je. right? We're not going to go into polar plot and the real and imaginary plot. You only choose one. Okay. So this is the magnitude and phase plot. You can see this?
Yes,
Because the
sir.
response of any network described as output amplitude, which is the gain, and output phase. Okay, nampak tak?
Gain, output, phase,
So
output,
this is the gain, right? And this is the phase, right?
input, gain. Okay.
So this is the omega. The horizontal axis is omega or frequency. The vertical axis it can gain or phase, right? So when you want to calculate the output gain, output amplitude is basically that the amplitude of the H j omega multiplied by the input amplitude. For the output phase, is basically that the phase of the response plus the input phase. Because remember, theta omega is equal to what?
Theta omega
Is equal to
Negative sign kan?
no. Yes, that is the formula, but it's actually the simplest one is the output phase minus input phase.
Oh,
Output minus input of the phase. This is equal to omega.
Oh, okay.
So that's why you want to get the output phase is basically the response phase plus input phase. This is only because this from the H is equal to V out over V in. So if you get the V out, so V in multiply H lah. Gitu je.
Sir, apa yang stop band dengan pass band tu, sir?
Stop band and pass band. This is when you come to the filtering. So pass band is basically that it pass all the signal. Stop band is stops from the signal. This one will we learn in the filtering. So let's say you have this function. Okay, this is the response. So this is the actual response of your systems. Say something like this. So this is the H, the gain. Okay, this. Okay, you have X, you have H, you have Y. Okay, so Y is equal to X times H. So let's say H, the value is V. So what is Y?
H value is V.
Is V.
X V.
So Y is equal to X V lah, the gain. But what about here? What is the Y?
Angle. Theta.
No.
No.
I'm asking Y, not the. I'm asking you the gain.
Zero.
Zero. Because Y is equal to X multiplied by 0. Because H is 0. So what happened? It stops the signal, right? Because it's 0. So that's why I call a stop band. This is the area where your signal is attenuated. So stop band. This is the pass band where you pass all the signal. The ideal filter is basically this, the dotted line here. This is the ideal filter. Okay, this is the ideal filter. This is called a low pass filter. It passes all the signal lower than frequency lower than omega c. And it stops all the signal higher than omega C. Right?
Okay, sir.
Okay, so that is what it means by pass band, stop band. So this we'll learn on the filter. Because filter, you have low pass filter, you have high pass filter, you have band pass filter, you have band stop filter. Those are the 4 basic filters. Right? So this one is actually a low pass filter because it passes the frequency below, it passes the signal below the cutoff frequency. Omega C is the cutoff frequency. If it's high pass, then it's the other way around. It stops the frequency below omega C and it passes signal, what call it, greater than omega C. This is high pass. Band pass, it passes only certain range of frequency. Band stop, it stops at a particular frequency but passes all others. So that we will learn in the next section. It's also in chapter 9 in the textbook, but after we cover the frequency response plot and body plots. Okay? Clear?
Clear, sir. Clear. InsyaAllah.
So for simplicity, normal ID response is used. Okay? This is actually practical data of a low pass. So it passes the signal below cutoff frequency omega C and it stops the other signal. So this is normally, this is a practical low pass filter. And for an ID low pass filter, it's basically, it has a very sharp drop here. This is an ideal filter. Anything below omega C, it passes all the signal without attenuation. Whereas in the practical one, it attenuates the signal. It attenuates the signal. So at this point, it's actually about 3 dB drop. So let's say this is the asymptotic, what we call it, line. So from here to here is 3 dB. Lebih kurang. V over square root 2 is about 3 dB, right? 1 over square root 2. How do you know? 20 log 10 of 1 over square root 2. Siapa ada calculator? Anybody can calculate that?
Ada, sir.
Huh?
Ada.
Okay. What's the value?
Ya, Apa tu, sir? 1 over
20.
20
Alah. 20 times log
times log
10 of 1 over square root 2. So take 1 over square root 2 first. Take the log 10, multiply by 20.
negative 3.01.
Yes. Basically, it's a drop of 3 dB.
Oh.
So that's why I say it's a 3 dB drop. It's because it's negative 3.01 decibel. So this is actually, the value is 3 dB. From V to V over square root 2 is about 3 dB because it's 3.01, right? So that is the drop. So that's why we'll take the corner frequency at 3 dB cut-off frequency, orang panggil. 3 dB cut-off frequency because of this. The actual one, actually this is the ideal. The ideal is here, the line is here at V. Then at omega C, it will drop 3 dB. So this is actually the actual value. So we'll take this as the cut-off frequency where you have a 3 dB drop of this signal. So basically, maybe this is in actual in ideal case, this is V here lah. And this a practical one is actually at this point it's not V anymore, it's V over square root 2 or 3 dB from V. Right? So this is the ideal low pass filter. So this in terms of phase is a straight line like this. At the omega C is actually minus 45 degrees. Okay. Okay. This is the ideal frequency response of a low pass filter. These are the 4 characteristics of frequency response of a filter. This is a low pass filter where you have a gain, and this is at the pass band, and at stop band you have a roll off. You have a roll off. Pasal lah saya punya ada line ada. Mungkin saya punya tablet tak elok kot. Okay. So this is a low pass filter. It passes all the signal below omega C and stop anything above, or it attenuates the signal. This is a low pass. For high pass, it's the other way around. It stops the low frequency. The ideal case is like this. This is the ideal filter. This is the ideal filter. But for the actual filter, it has a steady up and high pass is pass here. So this is actually stop band. This is the pass band. It passes anything above omega C. This is band pass. It stops this part and also this part, and it passes between omega 1 and omega 2. So the ideal band pass filter, it looks like this.
Dia kena lawan rasa.
Huh?
Dia kena terbalik low pass band.
Iyalah. Because low pass, you pass the low. The high pass, you pass the high. Band pass, you pass the this
band.
part. The part in between. Band stop, you stop one in between.
Faham sir?
Okay. So these are the 4 types of filters. Right? So band stop, basically you pass the one that is below the first cutoff, the lower cutoff frequency, and you stop the one in between these 2 cutoff frequency, and also you pass the one that is above the second cutoff frequency. So the ideal band stop filter is actually the response is like this. Macam telaga lah. Signal jatuh sini, datang sini jatuh semua kat sini, tak boleh keluar. Just fikir. You just fikir, band stop filter is like a telaga buruk. Where anything that go into the telaga cannot come out. So the signal basically within that range is 0. Macam telaga buruk. Band pass filter. Low pass filter. Low pass filter is like a gaung.
Gaung.
Dalam gaung ni tak ada out signal.
Out. Okay.
Kalau apa ni, low pass filter, you say gaung is on the right. High pass filter is gaung on the left.
Go on the left, on the right. Itulah signal. Okay, I see.
Kalau low pass filter is basically that you must have to be on the left. If you go to the right,
Pass.
jatuh.
You will down. Oh.
High pass filter, you must be on the right, because on the left, if you go to the left, jatuh kosong, jatuh gaung.
Kalau stop band, kita
Stop band. Telaga
Kalau-
buruk.
Okay.
Telaga buruk is in the between. Telaga. Sebelah kiri telaga, you are okay. Sebelah kanan telaga, you are okay. But in the telaga, no signal.
Okay, betul. Saya dapat bayangkan.
So band pass is basically you terbalikkan the telaga lah. I don't know lah apa benda.
Telaga tu kat atas bawah. Betul kan? Betul juga.
Basically band pass ini, you ada gaung kiri kanan.
Okay.
Eh?
Okay.
So it's for you to remember how the low pass filter looks like, high pass filter look like. So at least you have. So the border tu essentially is omega C.
Border is omega C.
Omega C or F. 1/F is T, yeah. So 2 pi F is the omega, right?
F
2 F is the omega. So if it's low pass, basically that the border sebelum you masuk gaung tu dia panggil omega C or FC. Sama jugalah dengan stop band and pass band, cuma stop pass band you ada dua omega instead of one, left and right. Stop band pun sama, left and right. Right?
Okay, sir.
Saya ngajar simple je.
Betul, sir.
So that you boleh bayangkan benda tu. Kalau nanti pening. So
Betul.
you draw this frequency response on a semi-log scale. It's normally used to plot frequency response. The gain, basically that is in decibel. So that's why just now I asked you to calculate 20 log 10 of square root 1/2, right? Basically I just want to show this. This is actually, if you want to indicate in dB, this is how you calculate. 20 log 10 of the amplitude H j omega. So will be in dB.
dB.
So remember this formula.
20.
This is when you want to convert from real number or from a number into dB. From unit into dB. Okay. Plot the frequency response for the network given. Semua boleh dengar? Boleh nampak?
Boleh, sir, boleh.
Okay. So you are given this circuits, and using the previous method, the magnitude of frequency response is given as this. Remember, this is actually 1/square root of 1 square plus omega over R/L square, right? Omega C was R/L. So magnitude is given as this. So this is your H of that. So you can calculate the magnitude in dB is 20 log 10 of this whole thing. See? So equal to 20 log 10 of 1 plus omega over omega C square. This one just rewritten this. So basically this is the magnitude in dB. So from there, then you can plot. You can plot the value and you can draw the graph. So the slope is actually 20 dB per decade.
20 dB per decade.
Yes. This per decade is basically this. On a log scale, this from here to here is 1 decade. So basically from 10 to 10 square is 1 decade. 10 square to 10 cube is 1 decade. This is 10 to the power of 0 here. So it dropped here is 20 dB. From here to here is 20 dB. From here to here is 20 dB. Okay. So if it's ID is what I call it body plot is basically is a straight line here, and over here is actually a drop of 3 dB here. That is 9, right? So if it goes smooth like that, is actually over here is 3 dB drop. You see this? It dropped 3 dB. 1 over square root 2. Okay.
Okay.
So nilai omega over omega P tu dia ambil kat mana?
This
Haa.
omega P is equal to what was the original? R over L.
Omega C, omega C.
This omega C lah. This is R over L, which is this one is okay, R over L. Okay, this is actually this is normalized lah. Normalized. If omega over omega P is equal to 1, then it's minus 3 over 0.1. If omega over omega P is 10, it's minus 20 dB here. If omega over omega P is 10.2, 10 square is minus 40. Yeah. So this is for the example of this is omega C or omega P is equal to R over L. What do you call it? RC. Where is the formula? 1 over RC or something like that, right? The frequency, the cutoff frequency. You go and do on your own study. Okay. Example 6. Find and plot the magnitude and phase of H1 of S equal to 1 over S plus 1. The first one. And the second one, H of 2S is equal to S over S plus 1. Verify that the magnitude are even and phase are odd functions of omega. So now, H1 of S is equal to 1 over S plus 1. And the steady state basically is H1 omega equal to 1 over 1 plus J omega. So the magnitude H of 1 is actually 1 over square root 1 plus omega square, and the phase is minus arctangent omega. Okay, this one you use you just transform this is S equal to J omega, that's all. And this is actually from the formula you can do to find the magnitude. For the second one, H of S equal to S over S plus 1. So therefore, H of 2 omega is equal to J omega over 1 plus J omega. Because you just change the substitute S with a J omega. So therefore, the magnitude is actually equal to omega square over the square root of omega square over 1 plus omega square. and the phase is actually pi over 2 minus arctangent omega for omega greater than 0, and minus pi over 2 minus arctangent omega for omega less than 0. This one you have to remember your previous math punya class lah, Okay. So how do you plot that? This is the plot. For the A, for this one, okay. For this one, basically that the what do you call it? It becomes bottom one is becomes 0 when omega is equal to 1. Right? In terms of frequency. But this is actually the plot for if you use the angular frequency in the what do you call it? So this is actually 1 here, right? So is up here for when omega is equal to 1. Then after that, it starts to, when omega increase, the denominator is increased. So H, what do you call it? The magnitude of H1 is decreasing. So basically that it start to go down. And the other side, so go down. So it's something like this. Ini apa dia ni? Okay. So you can do the plot. If you look at the previous slides, this one is not in the slide. This one, based on the text, it's actually example from the textbook. Just to show you how they plot the frequency response. And this is for this one. So if you look at this is actually, it's like a band pass filter, right? Something like that. So it passes at this frequency and it attenuates at this frequency and frequency. So it passes
betul.
this part. And this one looks like a band stop.
Laga buruk.
So for this one, S over S plus 1. So you have this equation, J omega over 1 plus J omega. So therefore, the magnitude is square root of omega square over 1 plus omega square. So it becomes 0, and that omega equal to 0 here. So the shape is something like this. So this one you can work on your own. This is actually an example from textbook. So that is the frequency response plot. And what we are interested in is the body plot, because this is actually very useful for plotting the transfer functions. Body plot actually invented by Hendrik Wade Body. Actually he lived from 1905 to 1982. He's an American engineer, researcher, inventor, and scientist. So basically, in the previous examples, required that each transfer function from the whole frequency range need to be plotted, and this is really time consuming. So you have to plot one by one for each frequency. But by using the body plot, you can actually simplify the plotting mechanism, because it's actually the body plot is actually a simplified frequency response using asymptotic straight line approximation. It's an approximation of the actual plot. So the body plot shows the gain of H omega in dB and phase theta in j omega versus the log frequency scale. Okay, so that is the body plot. So how do you do that? You determine the transfer function of the systems, H of S. So H of S, let's say, is given in this format: K multiplied by S plus Z1. Z1 is stand for 0. Z is 0. Not the zero number, it called a zero. Zero and poles. Right? And S over S times S plus P1. P1 is a pole. Basically, that a general transfer function, actually you have H of S is equal to K S plus Z1 S plus Z2 blah 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 divided by S plus P1 S plus P2 S plus P3 blah blah blah. So basically that this is a general transfer function, but to make it simpler, we just use this simple one. So let's say that you have this transfer function, and you rewrite this transfer function in the standard form of H of S K Z1 over times S over Z1 plus 1 and H of S and divide by H SP1 times S divided by P1 plus 1. So basically what you do is that you take out the Z. The top one you divide by Z, Z1. The bottom one you divide by P1. Okay. So that's why you get this. Where Z, S are called zeros, and the P's are called the poles. Z's called zeros and P's are called the poles. Right? What does that mean by zero? Anybody knows? What does it mean by zero?
Kenapa, sir?
You don't know?
No.
Don't know. Okay. Zeros means that the value of S to make the numerator equal to 0.
To make the numerator
Equal to 0. So in this case, S equal to Z1, right? Or
Okay.
Z equal to minus Z1, right? Then to the top one will be 0, right? So that's why it called a 0. It's the value of Z to make the numerator to be equal to 0. So that is a 0. A pole is the value S, in this case, to make the denominator equal to 0. So in this case, you have two. You have 0, S equal to 0, and S equal to minus P1. That is the poles. The top one, the zeros, is when S equal to minus Z1. So that is the zeros. So we indicate them as Z and P. Okay. So replace S with J omega, then find the magnitude of the transfer function. If we take log n of this magnitude and multiply it by 20, it takes down the form of 20 log 10 Hj omega. So it becomes this. So you expand, you get 20 log 10 of magnitude of K plus 10 of Z1 plus blah, 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 blah. Okay? So you kembangkan. Okay? So that is then you can plot this. Okay. Each of these individual terms is very easy to show on the logarithmic plot. The entire body log magnitude plot, the result of the superposition of all the straight lines. Remember class that I give an example of you add all the signals, the unit step and the ramp function that add. So actually that concept is you use in the plot where you just add. This means very little practice. We can quickly find the effect of each term and overall effect. To do this, we have to understand the effect of different terms. Okay. The constant terms K. K is actually a DC gain. It's known as a constant or DC gain. Constant. One, poles and zeros at the origin, where you have the magnitude of J omega. So if J omega is at the top, then it's a 0. If J omega is at the bottom, at the denominator, it's a pole. So for example, if you have h of s is equal to s over s plus 2. Okay? So this is the zeros at the origin. Or because s is actually convert into J omega. I like to use s instead of J omega. So this is a zeros at the origin. If I have a transfer function s of s equal to 1 over s multiplied by s plus 3, so this s is a pole at origin. Remember, the bottom one is poles and the top, the numerator is the zeros. Okay? Clear?
Clear, sir.
Okay. And the third one is poles and zeros not at the origin. So basically that these are the zeros, these are the poles not at the origin but at 3. Or it can be written this way. Basically this 1 plus s over p. Or this is actually p plus s. Prefer this one because I know already. I look at this, I know where is the location.
At 3.
Yeah. So if it's a 0, not at the origin, you have this example. H of s is equal to, let's say, s plus 4 over s plus 5, for example. So this is actually a 0, not at the origin, but it's at a 4.
Negative 4, negative 5.
So that is the 3 different types of terms. Constant, poles and zeros at the origin, and poles and zeros not at the origin. And how to treat them. The effect of a constant terms. The constant terms such as k contribute a straight horizontal line of a magnitude of 20 log 10 of k. So it's a straight line if a constant on your body plot. So you have a straight line throughout. But of course, you have to add after this. But if you take it individually, it adds a straight line. And effect of the individuals, zeros and poles at the origin. Okay? If you have zeros at the origin, so this is the origin basically at 1. This is the origin in the log scale. Not 0, because in log scale there is no zeros.
Zeros.
No 0. Because we go into 0.1 and 0.01, 0.001, 0.0001, 001. So you will never reach zero. In log.
Yes.
So this is actually 1 decade. From here to here is 1 decade. From here to here is 1 decade.
1 decade.
So this is actually 10 to the power of 2. This is 10 to the power of 1. This is 10 to the power of 0.
2
This
decade.
is 10 to the power of minus 1. So,
Minus
and over here is 10 to the power of 3.
3.
So it's 1 decade spacing. So for zeros at the origin, so basically that here, and the slope is positive.
Positive.
Positive. At 0.
Positive slope.
Positive slope, which is a rise of 20 dB per decade. So positive 20 dB per decade. Right? So this is for 0 at the origin. Right? For 0, for poles at the origin, it's the other way. Is
The other way. Negative
this
slope.
is actually with
Slope, slope, slope.
rise, this is decrease. Decrease, not rising. Decrease. A pole at the origin occurs when there is S or J omega multiplying the denominator. Each occurrence of this causes a negatively sloped line passing through omega equal to 1. It will decrease of 20 dB per decade. So it's decreasing per decade. So this is for a 0. This is a pole here. This H equal to 1 over S, or H equal to 1 over J omega. This one is H equal to S. Right?
H equal to S, H equal to...
Okay. So
Okay.
this is the poles and the
uh,
so this one I will correct. This is the third effect, which is not at the origin. Poles and zeros not at the origin. So zeros and poles not at the origin are indicated by 1 plus J omega over Z1 and 1 plus J omega over P1. The value of Zi and Pi, or this is I punya mata dah ni. In each of these expression is called the critical frequency or break frequency. Actually, where we have this here, this break. This is Zi, this is Pi. Okay. Below their critical frequency, these terms do not contribute to the log. So basically, it's here is 0. Above the critical frequency, they represent a ramp function of 20 dB per decade. Zeros give the positive slope, so it's going up. And poles will give a negative slope. So in this case, equal to 1 plus J omega over Z1, for example, 1 plus J omega P1. So Z1 is going up and P1 going down. To complete a log magnitude versus frequency plot of a body diagram, we superposition all the lines of the different same. After that, you add those lines together. Right? So, for example, to give you an example, let's say you have a transfer function. Everybody can hear me?
Yes, sir.
Okay. That
Yes, sir.
body log magnitude diagram, which shows how the log magnitude of the system is affected by changing input frequency. Let's say you have this transfer function. H of S equal to 1 over 2S plus 100. Okay, how are we going to find this? This essentially can be written as this. How to do that? You must you divide by 100 top and bottom. Right?
Alright.
Both you divide by 100. Okay?
Okay, sir.
So when you divide by 100, you have h of s is equal to 1 over 100 divided by s over 50 plus 1. And you recognize this in this form actually.
Yes.
So K is, this is the K, 1 over the 100. And 1 over P1 is 1 over 50. Okay? So K is 0.01 and P1 is 50. Okay? So from here, for a constant K, you have a straight line of minus 40 because 20 times log 10 of 0.1 is minus t.
0, 1.
So a straight line at minus 40 dB. So you get this red line.
Right. Straight line.
Straight line. Then for the pole of P1, which is at 50 just now, so you go to the 50 at omega scale 50.
Omega.
You find the 50, then you draw the dotted line here. Basically 0 dB until it reaches 50, then it drops by 20 decade. 20 dB per decade. Okay?
Sir, kenapa dia ada dua orang, sir?
Yang mana?
Yang satu untuk satu pole, satu.
Yes. So no. There is no pole, but there is no zeros. Okay. So basically that this red one is contributed by K.
Okay, alright.
Alone. There is we don't add yet.
Okay.
And this dotted line here is contributed by
P1.
P1. Then after that, we add these two. We add the dotted line here. So from 0 to 50, basically that 0 add with minus 40 is minus 40. So you get this line. This is the addition. This is the black one.
The
up
black
to here.
one.
Okay. Then it starts to go down, right? So it becomes minus 40 add by minus something. So that's why it goes down by this one. It's parallel to this one.
Parallel.
Because this is actually drop of 40 dB. Okay. Because of this drop. Because of this from here to here is the red line.
So the final
The final one is the black line.
The black one. Okay.
Yes, this is the final line. Right?
Okay.
So basically that your circuit has a attenuation of minus 40 dB. Your system actually give you a minus attenuation 40 dB. Okay, that's how you do a body plot. Second example, you are given this frequency, this transfer function. H of s is equal to 5 times 10 to the power of 4s divided by s squared plus 505s plus 2500. So from here, we need to simplify the transfer function in a form that we can recognize. Okay. Normally, basically, we need to transform into this format. Okay. S plus Z1, S plus Z2 divided by S plus P1, S plus P2, So basically that we want to write into this format. Okay. Whatever it is, we try to write in this format. So in this one, we can write the top one is we don't because we only have s, so therefore we can write 5 times 10 to the power of 4 of s. Divide by the bottom one, this one you factor, you get s plus 5 times s plus 500. Okay. So this one you have to do the math. Then this one you try to write in the form of
Can understand.
s over p1 plus 1 s over p2 plus 1 in this form. So that's why this you divide by 5 and multiply by 5. So this one you divide by 500 and multiply by 500. So you get in this format. So basically now you have k ks over s over p1 plus 1 s over p2 plus 1. So basically that you have k is 20. You have 0 the origin. Okay. This actually give you the 0 at the origin. Okay. And you have a pole 5 and 500. So you have how many lines? 1, 2, 3, and 4. 4 lines. This 0 is at 0 at origin.
Okay.
Okay. You can count how many S's that you have. 1, 2, 3. So basically that you have 3 sloping lines. And this one is the K with the constant. Okay. So you have 3 sloping lines and a constant.
Just like that. Okay.
So that is the beauty of body plots. From the equation you can approximate the plot of your response of your transfer function. So tadi I cakap K is 20, right? Yeah, I say K is 20. So then you transform into the in dB, so it's equal to 0.02 dB. Okay? And you have 1 0 at the origin. Okay, this I say 0 at the origin. Okay, so that and 2 poles, 1 pole at P1 and
500.
P2 at 500. See at 5 and 500. Yeah, so you get that. So this is what to do. Okay, for this one is this line. This
0.
It's not 0. It's 26.02.
601.
So line 0 is here.
Okay.
So this is at 20.0602. This line. This dotted line,
Dotted line. Okay.
This. So it is the contribution from K. The second one is at the origin. Poles at the origin. Okay, at zeros at the origin. So which line?
Zeros at the origin.
Where is the origin? What does it mean by origin?
0 barangkali. Oh no.
No, log mana ada 0? At the origin is 10 to the power of 0.
10 to the power of 0.
It's a log scale.
Origin.
This is the origin.
Okay.
10 to the power of 0. This is the origin.
Okay, sir.
Not here. This is not the origin. This is actually 10 to the power of minus 1.
Okay, sir.
Okay. So
Alright.
10 to the power of 0 is the origin. So at the origin, the value is 0 dB here. Okay? And you know that for 0 is increasing 20 dB per decade. So this is 20 dB. So this is actually minus 20 dB per decade. So from here, reduce by 20 dB and up actually 20 dB, 20 dB, 20 dB, 20 dB. So this line is contributed by this, one. Zeros at the origin. Okay, so now you already have two lines. This is by K and this is by the zeros at the origin. The second one, P5. P1 is at 5 is a pole. So where is P5? So this is 10 to the power of 0, which is 1, which is 1.
1.
So 2, 3, 4, 5. So this is the P equal to 5.
5. Oh, macam tu.
Okay. So 1, 2, 3, 4, 5. Lebih kurang lah. So this
Okay, sir.
this line, this okay.
Okay.
So here. So at 5 here is 0, below than 5 is 0. Okay. And greater than 5, it reduces by 20 dB per decade. So this is the line. This line is contributed by the P1 curve line here. Okay.
Okay, sir.
And the fourth one, the fourth curve is contributed by P2 at 500. 500, basically this 10, this is 100. So if this is 100, if this is 100, so this is 200, 300, 400, and 500.
100.
This here, it break here. So anything below 500 is 0
Zero.
dB. And anything above 500 radian
Slope
is sloping negative by
negative.
minus 20 dB per decade. So this is actually contributed by P2. So now you have drawn all the lines individually. Now you have to add. So from here, you can see that, okay, at here, you have minus 20 dB, you have 20 dB, which is 20 dB, and another one is 26.02. So 20 minus 20 plus 26.02 is 6.02, right? So it's about somewhere here. Because this is actually 20. This is 20. Because this is 40. So this is about 6.02 here. Then it increases because of this contribution from the 0 at the origin. Okay, so it's parallel with that. It's increased until it hits the P equal to 5 here. Until it hits there, then it start to cancel out in these two. The zeros and the P1 cancels out. So it's flattened. Okay. It flattened out until it reaches at P equal to 500. When it reaches at P equal to 500, then you have the contribution from the P2. So it reduces by 20 dB per decade. So the resultant curve is this black one. Okay. So this is actually looks like a band pass filter, right? Because it passes the signal from 5 radian into 500 radian. and the red, and in between, outside than that is attenuate the signal. So this is a pass filter with a gain of 40 dB. It's an active filter. Actually, because it's an active filter because the gain is greater than 0. Greater than 0 dB. Okay.
Alright, sir.
So this is actually a band pass filter.
Band pass filter.
So this is how you draw the body plot. Okay. So this is actually the what I call it, I just draw here. Eh? So this is the step. Actually, if you sketch by hand, actually we have go through that steps. First, you identify the poles and zeros of the system. That's what we did. From the equation, we try to put into form that we recognize the poles and zeros. Then after that, we take the semi-log paper and we draw the horizontal axis and the vertical axis. And we mark the axis, the corresponding points in terms of poles and zeros. That's what we did with P1, P2 just now. Then we start from then to plot contribution from each what I call it, poles and zeros individually. Then after that, we start to add them. We draw. We start to do addition. Okay.
Okay, sir.
Then basically that we recognize the breakpoint and whatnot. So we can sketch and improve the using the value of the magnitude and frequency of what we call it, minus 3 dB and 3 dB, those kind of thing. So you can what we call it, smoothen out the curve. Just now we just give the asymptotic lines. So if you use the to smoothen this curve, basically that you can draw is actually over here is actually it will drop about 3 dB. Here, to drop at 3 dB at this corner here as this knee. This also 3 dB. So the curve is something like this lah. Follow nicely here, then start to drop. Then after that, follow nicely here and drop. Follow nicely. So it's smoothen. Okay.
Okay, sir.
That is the body plot. What time is it now?
Oi,
Sir, 11:05. 11 lebih dah, sir.
Sudah lebih dah. Okay.
dia tengah sangat tu.
So basically, basically that we complete the frequency response and body plot.
Okay, sir.
So dah ada yang tidur dah?
Tak ada lagi, sir.
Tak ada lagi. Okay. Ada yang mengantuk?
Ada, sir. Saya,
Ada
sir.
lagi, sir. Esok bangun lambat kot, sir, dia tu.
So that is the frequency response and body plot. Any question on that?
No,
Simple,
sir.
Simple.
Simple,
sir.
sir.
Tapi susah.
Simple susah.
Yeah.
Simple senang.
Simple. Simple is mudah.
Simple is mudah, sir.
Mudah. Mudah tidak semestinya senang. Mudah tidak semestinya senang.
Tengok muka Pak Is. Kesian Pak Is. Pak Is tengah belajar lagi.
Mudah tidak semestinya senang.
Mudah tak semestinya senang. Kiranya dia CCU, ICU.
Ehsan dah lewat. Ehsan dah fikir yang mudah tu mestinya senang.
Tidur dulu. So tomorrow we go into analog filter. Then basically we finish all the analog, and we do the what I call it. Most of the, let's see, kalau test tak masuk analog filter, maybe we'll do the revision ago. Tengok macam mana.
Baik.
Kita revisi sampai dah pro baru kita buat tutorial. Mantap je.
Most probably that test in 2 weeks time, week 7. Now 5th, number 5. So we have next week is 6, then 7. Most probably that we'll try to push to the test to week number 8 lah kot.
Push 8 lah sir, 8 lah.
Tengoklah macam mana. So, okay, any question?
No sir.
No, sir.
Yes, apa tu bunyi? Tak ada. So, okay, kalau tak ada, then we can stop our lecture today.
Thank you, sir.
Yes.
Apa je tadi je?
Thank you very much, sir.
Okay. Thank you. I'm going to stop the recording and see you tomorrow.